Welcome to lecture 12. In this lecture, we're going to calculate some examples where we can evaluate these Christoffel symbols that we talked about in the context of the geodesic equation. So recall that in the last lectures, we discussed the geodesic equation, which is reproduced here in equation 12.1. This is a second order differential equation on the coordinates, and it involves these Christoffel symbols gamma, mu, alpha, beta as part of the equation. In the last lecture, we found an expression for the Christoffel symbols in terms of the metric tensor and its derivatives. It is reproduced here in equation 12.2. And in this lecture, we want to give examples of how one can calculate these Christoffel symbols in practice. First, let's have another look at the definition of these Christoffel symbols. What you should note is that in this expression here, the indices alpha and beta appear symmetrically. So here we have G alpha beta, take the metric to be symmetric. Here we have beta, d beta, G alpha gamma, and here we have d alpha, G beta gamma. So basically alpha and beta here are symmetric. It's also symmetric here. So that means that the Christoffel symbols are symmetric in the lower indices alpha beta. In four-dimensional spacetime, the Christoffel symbols have three indices. So that means they can take 4 by 4 by 4 values or components. That's 64 for four-dimensional Minkowski space. However, because these low indices alpha and beta are symmetric, it means that not all of these 64 components are independent. It so happens that the part, this 4 by 4 matrix part that is representing the lower indices, only the symmetric part of this contributes. So we get the independent contributions from the diagonal, which are 4, the superdiagonal 3, the superdiagonal of that 2, and the uppermost right corner of this. So in total, we have 10 independent components from this 16 symmetric entries. So we get 4 for the upper times 10 components is 40 independent components of the Christoffel symbols in four-dimensional Minkowski space. That's still a lot of components. So basically what that means already there is that if we are trying to solve the geodesic equation in four-dimensional systems, then we always have to calculate these 40 components which are independent. So that is hard work. We want to get started by treating simple examples where it's easy for us to calculate all of these 40 components. And one of these examples is indeed just empty Minkowski space. So we have talked about the metric of Minkowski space being just a diagonal matrix and has entries -1, 1, 1, 1 along the diagonal. I write the diagonal matrix simply by this expression diag here. So because the metric has just entries that are constant, the derivatives or all derivatives of the metric vanish because any derivative of a constant is just 0. And that's good news because since the Christoffel symbols contain only derivatives of the metric, that means that if the derivatives vanish, then all Christoffel symbols are identically 0 for Minkowski space. So in this case, it was easy to calculate all of these 40 components. If the Christoffel symbols are all 0, the geodesic equation simply becomes d squared x mu by d tau squared is 0. And that's just the statement that a particle with no force in Minkowski space will travel with constant velocity along a straight line. Now let's aim for a slightly more involved example. And for that, we want to use polar coordinates in 2 dimensions. So we have coordinates x mu being r and phi. We have already calculated the metric tensor for polar coordinates in lecture 9. Specifically, have a look at equation 9.12, where we found the expression for the metric tensor in polar coordinates to be given by a diagonal matrix that has an r squared in the lower right component. Note that I'm writing G mu, even though normally I have been using Latin indices for positive definite metric signatures. I want to stick with this mu simply because I don't want to rewrite the notation for the Christoffel symbols. So I'm slightly abusing my own notation here. Now let's take this metric and calculate the Christoffel symbols for this metric. So because we have symmetry in the lower indices, and because we're in 2 dimensions rather than in 4 dimensions, we have a lot fewer components to calculate. So we're in 2 dimensions, so the upper index mu can take 2 values, and the symmetric part of a 3 by 3 matrix the symmetric part of a 2 by 2 matrix has 3 independent components. So we have 2 times 3 is 6 independent components for the Christoffel symbol. Explicitly, we can write these out. So we have gamma r, 3 of them, with RR, R phi, and phi phi in the lower indices. And then we have 3 with a phi upstairs, and these are RR, R phi, and phi phi, again, in the lower indices. Let's go and calculate them. Let's first pick gamma RRR. Using the definition of the Christoffel symbols that we have found in the last lecture, we can write down an expression that involves the metric, the derivatives of the metric, and the inverse metric, so basically the metric with upstairs indices in polar coordinates. So let's look at the inverse metric first. Since the metric in polar coordinates is diagonal, writing down the inverse of the metric is easy. G mu with upstairs indices is just the inverse of the metric with these upstairs indices, and the inverse of the diagonal metric is just 1 over the diagonal entries in the matrix. So the inverse metric has a 1 over r squared instead of an r squared in the lower right component. So the inverse metric is also diagonal. That means that only some of the entries in gamma RRR survive. I've written them down here using the fact that the metric here is diagonal. We get 3 times the same expression, twice with a positive sign, once with a negative sign. So that means we get 1/2 derivative of GRR here. Now we know that the element GRR for the metric in polar coordinates is just 1. So the derivative of 1 is 0. So that means that gamma RRR is just 0. Next up is gamma R phi. That's given by the following expression using our definition for the Christoffel symbols. Once again, we use the fact that the metric is diagonal. So basically, this means that every occurrence of gamma in the downstairs matrices here has to be replaced by R, because that's the only non-vanishing metric element up here. So we find that gamma R phi is given by 1/2 derivative with respect to R of GR phi, d phi GRR, and minus dr GR phi. However, the metric is diagonal. That means that GR phi is 0. So these 2 terms just vanish, and we get 1/2 d phi GRR. However, GR is constant, so the derivative of a constant is 0. So we can find that also gamma R phi is vanishing. Next up is gamma R phi phi, which has the following expression from the definition of the Christoffel symbols. You know what's coming. The metric is diagonal, so that means that the expression here simplifies to the following form here. We have still the entries GR phi in the derivatives down here. Again, these entries are 0 because the metric is diagonal. So we end up with minus 1/2 dr g phi phi. However, g phi phi is r squared. So taking the derivative of r squared is just r, and then 2r, and then together with this factor of minus 1/2, we find that gamma R phi phi is just minus r. Finally, a non-vanishing result. I was getting worried that we would get zeros for all Christoffel symbols in all cases. So we find that it's not that hard to calculate the Christoffel symbols, and we could go on and calculate the 3 remaining ones, the one with the phi upstairs for polar coordinates. One finds that only one of them is non-vanishing, and we find that in total we have 2 non-vanishing Christoffel symbols for polar coordinates. One of them is the one we calculated, gr phi phi, and the other one that we didn't calculate is gamma phi r phi, which is 1 over r. So yes, everybody can calculate Christoffel symbols. It is kind of tedious. In fact, it's not only tedious, it's actually mind-numbingly repetitive. And that's bad, because what that means is that people are not good at mind-numbingly repetitive tasks. And what happens is, if people try to calculate Christoffel symbols by hand, is that invariably people will make errors because it just breaks you down. So the question is, who is good at performing mind-numbingly simple algorithms for a long time without error? And the answer to that is, of course, computers. Computers are very good at doing stupid jobs. So we will discuss a computer package, so-called efficient symbolic manipulation packages for general relativity in the next lecture, that will basically help us with these stupid tasks of calculating things like Christoffel symbols that one can do by hand if given enough time, but which is completely pointless, because all it will happen is that it will take a long time, and a computer can do it much better, and there's nothing to be gained by calculating it by hand. So that's what I was saying, and this concludes the first lecture, and we'll talk about how to set up this manipulation package in the next lecture.